Hi, this is Mrs. Robel. This is part 4 of electrons and atoms. So far we've discussed what is light, how do we describe it. When we're looking at electrons, we need to look at the energy levels. What's the frequency, what's the wavelength. We've looked at the Balmer, Lyman, and Paschen series in hydrogen. Now we're going to look at the electron. How does the modern atomic theory treat it? We're sort of looking for the address or the location of the electron because that's going to be important for us when we look at things like chemical bonding. Now, before I go into details about Schroedinger, whose picture you see on this slide, I want to show you some examples of models of electrons and where we think they may be located. So with this model, I'm going to show you the Bohr model, and this is something that you've seen before. The only difference is I have this energy level diagram, and you can see where the electron goes from the ground state to the excited state and then back down. You may notice when it goes back down, you see a photon of light that's being ejected, like right there, or right there. Remember, he treated it as orbits around the nucleus. Now here is a man by the name of de Broglie. We talked about him a little bit a couple videos ago. So here you actually see a wave vibration according to the energy level that the electron is located in. So de Broglie is treating the electron movement as a wave function. And notice that depending on what energy level it is, it has a certain vibration according to that energy level. Now here's the last model that I want to show you. This is called the Schroedinger model. And if you notice on the energy level diagram, it's significantly different from the one that you just saw with de Broglie. And if you notice too, the way the model is drawn, it looks like clouds, and it may look like it has a top and a bottom. And notice when the electron goes from ground state to excited state and then back down, it's giving off photons of light, just like we discussed in previous videos. Also notice that with the energy levels, we have, for energy level 1, we have 1 slot. For energy level 2, we have 2 slots. Energy level 3, 3 slots, and so on. We're going to talk about why does each energy level have an increasing number of slots. Okay, so let's go back to Mr. Schroedinger. So Schroedinger was a very wise, mathematically inclined physicist. And what he did is he described the electron as dualistic. And what he meant by that term is, gee, this is a familiar theme. Sometimes the electron can be seen as a particle. So remember how we talked about light acting as a particle, as a photon? Well, guess what? We're treating the electron in a similar fashion. Also, Schrödinger treated the electron as a wave. And the wave, we can actually tie that into de Broglie. I don't know if you remember, you saw it with the wave functions or the movement of the electron in a wave vibration. So Schrödinger, he saw the electron essentially as a particle or a wave. So what he did is mathematically, he took that electron and he described it as a three-dimensional standing wave. We're getting into some really heavy-duty math here. This is something that a lot of physicists struggle with to try to describe to people in non-math terms, and it's very challenging to do that. I'm going to show you some pictures of one-dimensional standing wave and a two-dimensional standing wave. If you're a musician who plays a stringed instrument, you may have seen these vibrations when you pluck a string. Okay, so here are some examples of standing waves. And these pretty much come into play with sound. So when you have a vibration with a string, you could have essentially half of a wavelength. So this is for n equals 1. Notice that when we change the energy level, we're increasing the amount of energy here. We have essentially a set of 2 half wavelengths. For 3 energy level, we essentially have 3 half wavelengths. Now, notice that this is associated with a guitar string. So if you were to pluck it with the right frequency, you would essentially get these type of standing waves. Now, with an orbiting electron, it's a little bit different here, but we're almost incorporating the same thing. So the bottom left-hand side almost is similar to the top right-hand side. The only difference is we're talking about a circle as opposed to a straight line. Notice with n equals 5 wavelength, we're increasing the amount of half wavelengths that we have within that circle. Notice that n equals a whole number is not allowed, and that'll make more sense when we talk about things like quantum numbers. Okay, here we go. So like I said, Schrodinger's treatment of the electron is very challenging. It's essentially pure math, and I've done some of the math. It can give you a headache. So we're talking about pure math, and you need calculus to describe this. So he's actually creating an address for the structure of the atom. This address has what we call quantum numbers, and these quantum numbers are included in the equation that Schrodinger uses to describe where the electron is. Now, this is something that is very difficult to understand sometimes. This actually gives you a probability that the electron is in that location. What this means is we don't know at that instant the exact location. We know there's a good chance that that electron is going to be found in that location. So it's a very nebulous type of treatment with the location of the electron, but the math works. Okay, so quantum numbers are going to be your friend with this part of the chapter. What does this mean? Well, that means for the address, when we are describing where the electron is, we first have to look at the n number, which is the energy level. So remember how we were talking about the Lyman, the Paschen, and the Balmer series? They all had energy levels that are associated with each type of series, and we're using the same energy levels for that to describe. What this means is the higher the energy level, the more distance the electron is from the nucleus. Now, this next number is what we call the sublevel. So the first part of the address is called the quantum number. The second part is the sublevel. So this actually tells us the type of vibration. I always think of it as like an electron cloud, and it'll make more sense once I show you some of those shapes. But we're looking at the shape of the sublevel. So each sublevel actually has a specific shape associated with it. Okay, so notice that if we have one energy level, we only have one sublevel. So that diagram or that model that I showed you for the Schrodinger had one slot. Here we have energy level 2. Notice that there's 2 slots. There's a 2s and a 2p. For energy level 3, there are 3 slots. So there are 3 types of sublevels. And notice for energy level 4, there are 4 slots. For energy level 5, there are 5 slots. So if you had to guess for energy level 6, how many slots will there be? Correct, there'll be 6. Okay, so After we've looked at the first two quantum numbers, we need to look at a third type of quantum number, and this is called the magnetic quantum number. What it does is it describes the orientation of the sublevel. So we're breaking down more information. We know what the sublevel is now. The additional piece is where is that electron located within that sublevel. Now, notice that if there are n squared orbitals, there's that per energy level. So notice that S has one orbital, P has three orbitals, D has 5, F has 7, G has 9. So these sublevels have that many orbitals within that sublevel. And it'll make more sense in a little bit. The last quantum number is called the spin quantum number. And what that means is essentially is the spin up or down. So notice if it's positive, it's located, if you want to look at the planet as an example, notice that it's pointing down if it's positive, it's pointing up if it's negative. Okay, so this ties in with the vibrations that you saw when I was showing you some of the models, more specifically the Schroedinger model. So notice the Schroedinger model, when we're looking at an s orbital, we're essentially looking at a sphere. So if you want to think of it this way, whenever you see the s orbital, we're talking about a sphere. You can only fit 2 electrons in this sphere. So no matter what the energy level is, it could be n equals 1 all the way up to n equals 7, for instance. Each s orbital will only contain 2 electrons. Now, for the p orbitals, this is where it gets a little more complicated. We have a total of 6 electrons, and there are 3 main orbitals. So notice that there's a px, a py, and a pz. Now, all this means is that the p orbital is on the x-axis, or the y-axis, or the z-axis. And when you put them all together, it sort of looks like a flower. In each p orbital, each subtype, you can fit 2 total electrons. Okay, with the d electrons, once again, we're building complexity here. We can have a total of 10 electrons. Now the good news is I will not ask you to draw these type of orbitals, but just to let you know, we're talking about the orbitals are along the xz axis, the yz axis, the xy, the x squared minus, that should be a y squared, that's a typo, and then z squared. So please notice there's 5 different possible locations, and each subset of the suborbital can contain 2 electrons. So even though there's 4 lobes, you can only put 2 electrons in those 4 lobes. Okay, yes, we can get even more complex, which is amazing. Nature has a very interesting way of making itself very challenging to understand. So here we have 14 electrons. So this is the f orbitals, and yes, it gets even more ridiculous with the type of drawings. So even though there's, let's see, 1, 2, 3, 4, 5, 6, 7, 8 lobes, you can only fit 2 electrons in those lobes. But notice there's 1, 2, 3, 4, 5, 6, 7 different types or subsets of the f orbital. And these are essentially the mathematical equations that you can get from the location. And this is probability of the electron. So we don't know for sure where exactly the electron is, but we have a good idea that it's probably within that region. Okay, so what I want to do with you is I want to show you how to figure out what element based on the quantum numbers, and then if you have the element, how do you write the quantum numbers? So I'll do the first three, and then the last one you'll do on your own. So notice that here we have n equals 1, the first principal quantum number. This tells us the energy level, how far away the electron is from the nucleus. L equals 2, so azimuthal, this tells us what type of sublevel or suborbital we're dealing with. M sub L, so this is the magnetic quantum number that tells us within that suborbital where is the electron found, and then S tells us the spin. So what I'm going to do is I'm just going to write the number 5 here off to the side, and I'm going to figure out what suborbital are we talking about. Now, just to let you know, L equals 0 is the s orbital, so it's not that. L equals 1 is the p orbital. L equals 2 is the d orbital. So this is 5d. And the question is, we have 1 as the number. Now we have 5 slots for the d orbital. And when we figure out where's the electron within these slots, we're going to take the negative value of the the azimuthal, and we're going to make it all the way positive. So we go from a -2 to a +2. So this is a this is a +1, so the location for the electron has to be in the 4th slot. Now the question is, how many electrons are we talking about? We have a +1/2, so this means that the electron is spinning clockwise, and we call that spin up. So we're going to essentially fill out each subset of the suborbital up to the +1 subset. So we have 4 electrons here because it's a positive or a clockwise spin up. So the quantum number represents 5d4 electron. Now this still doesn't tell us where the element is. So I'm going to go to my periodic table here. So when we look at the periodic table, so each row is a period. So this is period 1, period 2, period 3, period 4, period 5. Now we have to be careful because the energy levels actually change when you go across a row. This yellow section here is the d electrons, and they actually start numbering at period 3. This is period 4 by yttrium, and then here's period 5 by lanthanum. Now we have 4 electrons, so we want to count over 4 spaces, so 1, 2, 3, 4. So our 4th electron is actually tungsten. So let's go back to our problem here. So we're looking at 5d4, which is actually tungsten, which is a W. And this is actually metal that is found in the light bulbs, incandescent light bulbs. Okay, so that is the quantum number for tungsten. Now we have to look at cadmium. So cadmium, what we have to do is we have to go to the periodic table, and we need to figure out what energy level. This will be the last electron within that atom. So we're not describing all the electrons within the atom. We're only looking at the last electron in the atom. So we're going to look at the periodic table to figure out what is cadmium. Okay, so going to our periodic table, I'll tell you right now, it's in the transition metal section. So it's in this yellow section here, and here it is right underneath zinc. Okay, so I told you this first row of the d electrons is period 3, Therefore, this second row is period 4. Notice that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons within this row, and this represents cadmium. So let's go back. Okay, so I said cadmium is in the 4d electrons, and there's a total of 10 electrons. So for the energy level, we're going to give it a 4. If it's a d orbital, we said that it has to be L equals 2. Now the question is M sub L, what is that going to be? Well, I'm just going to draw my 5 slots here. 1, 2, 3, 4, 5. Remember, I said there are 2 electrons per slot, so I'm just going to draw 1 electron first. These are all the positive spin or clockwise electrons. And then I'm going to start adding 6, 7, 8, 9, 10. Now remember I numbered them across. So this is -2, -1, 0, +1, +2. So this very last electron is actually in +2 magnetic number. Now it's a spin down, which means it's counterclockwise, so it's going to be a -1/2 quantum number because it's spin down. Okay, so last one, we're doing sulfur, and I'm going to go back to my periodic table. So when I look at sulfur, sulfur is in this region. This is actually the P region of the periodic table. So here's the S region, the yellow's the D region, and this is the P region. When we look at the rows, so this is period 1, period 2, period 3. So notice that sulfur is in period 3. We don't have to worry about any numbers changing when we go across until we get to the d orbitals. So this is the period 3 p orbital. And the question is, how many electrons are in the p region? I have 1, 2, 3, 4 when I count across. So I have 4 p electrons. Okay, so solving this, I said that I'm talking about the third energy level. L, the azimuthal, it's not a D, so it's not 2, therefore it has to be 1. And then the M sub L. Well, we'll have to draw the slots for this one. So 1, 2, we only have 3 slots. And, you know, I'm going to make this a darker color because this looks kind of hard to see. So we have 1, 2, 3 slots. And we're going to take the 1 and make it a -1, 0, and a +1. Now, I said that I had 4 electrons, so I'm going to draw the first 3 electrons up. They are clockwise. And then the 4th electron is pointing down. So the magnetic number is going to be a -1. So M sub L is a -1. Because it's a spin down and it's counterclockwise, it's a -1/2. So energy level 1, suborbital 1, magnetic spin -1, and then spin 1/2. Okay, and then you will do the bromine magnetic, or I'm sorry, quantum numbers on your own.